Good afternoon. I'm Aman, and what I'm going to present is an immersive debugger for actor programs that I developed over the course of my master thesis at Max Planck Institute for Software Systems in Kaiserslautern, Germany. So essentially, the motivation behind this immersive debugger was that the debugging or comprehension of actor programs is really difficult. So if you're not aware of of what an actor program is, these have become really popular of late. So this is just a model of concurrent programs. Essentially, you have independent lightweight actors that do something, and they interact with other actors via asynchronous messages. Now, obviously, as you know, as these number of actors increase, as well as the messages that they send between each other increase, you have huge traces. And it is really difficult to understand such a long trace, and if there is a bug, essentially what you have is a very angry programmer. And what we propose is an immersive debugging environment for these actor programs, so that you have actors instantiated as 3D entities in this virtual space. You see messages being sent from one actor to the other as arcs in this 3D space. What you could do is also set breakpoints on the message level, and you could visualize, for example, the message box, the mailbox, and states of these individual actors. The end goal, of course, is to have happier programmers. To just give you an overview of the interface, so essentially these actors are instantiated in this 3D space. Obviously, it's you could just assign any 3D model to this. So actors of the same class, for example, have the same 3D mesh. You have these visualization metaphors of whenever an actor is active, you have that outlined so as to guide attention to it. These message arcs are visualized in this 3D space whenever a message is sent. These colors denote the behavior of this actor, and the behavior is essentially how would an actor process a message in its mailbox. You could look at the states, so the local variables inside this actor, as well as the number of messages it has in its mailbox and the next message this actor is going to process. And these in general are the features. So you could query an actor state, so you could just point at an actor and ask what its state is. You could move forward and backward in trace, so you could move a few steps back and just look at the trace again so as to comprehend it better. What you could do is breakpointing on the message level, and this is different from what traditional IDEs offer. So traditional IDEs offer a statement level breakpoint, but with a message level breakpoint, what you want to say is that notify me whenever this particular actor receives a message. So whenever, so the program would just essentially execute until that particular actor processes a message, and then you would be notified and the breakpoint would be hit. What you could do is manipulate a schedule, and this could be just to check the robustness of the system in general. So what you could do is let's say you're at some point of the trace, and then there is this non-determinism in this actor world, and this non-determinism of which actor proceeds next is on the number of actors that have messages. So what you could do is ask the system what would happen if, let's say, this actor proceeds next, and then this actor proceeds, or let's say what happens if this actor drops the message that it currently has, so as to just poke around the system and see how things proceed. What you could do is track causality. Conceptually, this would mean is you could mark certain actors as red and mark certain other actors as blue, and what you could do is whenever a red actor sends a message to another actor, this other actor also becomes red, and you could see this causal chain evolving over time. And with this, what you could also do is look at interleaving and race conditions better. So there are a few other features, but these were the most important ones. So just few photographs or screenshots from the system, and I hope to see you at the poster. Thanks.
Any questions?
Yes.
Do the three dimensions of the three-dimensional space have a particular meaning?
So they currently don't. But I do agree that if we were to use the 3D in a better way, so for example, the idea behind, so though we did not look at how to use 3D, but the idea was that perhaps you could use this for IoT applications wherein they actually have a geographical location, so you could use these geographical locations as such. Also for CPS systems wherein these things could actually move over time, and then you could visualize these nodes actually moving. However, the only examples that we've tackled so far are abstract actor programs. Something else that we haven't thought of is visualizing time better. So if we do have abstract programs, perhaps 2D is better, but then you could use the third dimension to show time in a better manner. But I do believe that this is not the best time visualization tool. Yes.
Feasible is this for actual debugging if you just don't have it, like for example, but like a big program with many actors or whatever?
So we tried to debug this tool called Gatling, which has somewhere around 16,000 lines of code and around 12 actors, and we were able to successfully do it. It is the case, obviously, that if you write a program from the beginning, you more or less know what these actors individually do, and the kind of problems we tackle and we hope to tackle is these message sequencing problems. So the idea would be that, so these toy examples, the reason we chose them was you can debug them because you know what each tiny toy does, and it's just this message sequencing that you need to solve. But yes, if you're writing a program from scratch, you already know what each node does, and we hope that you can essentially debug these incorrect sequences in a better manner.
Is this your pen drive?
No, this is for the pointer.
This is for the pointer? Okay. And thank you. Hello everybody, I am Abhishek Kumar Singh from Tata Institute of Fundamental Research, Mumbai, and this is a joint work with my supervisor, Raja Natarajan. So this is a bit off the track, so this is not automated theorem proving, this is actually work in interactive theorem proving, where we work with the theorem provers. The word theorem prover itself is misleading, it's a proof assistant, and I did this work on a Coq proof assistant. So there is less of automation here, more of interactively proving theorems. So it's a theorem prover based on type theory, but you don't need to know much about type theory to use this theorem prover. You can write down mathematical statements in this theorem prover and prove their correctness. So the good thing is the Coq team already hosts a standard library which deals with primitive things like sets, numbers. So you can start using it without knowing anything about type theory and prove some beautiful theorems. So this is the major advantage, that we have a standard library. So our work is an extension in the same direction. So there was something missing in the standard library. So it has many implementation of sets, different kind of implementation of set theory. So we extended it to and took it to posets. So we developed a small library which deals with definitions and some facts on partially ordered sets, and we completely we only use the ensemble module which deals with set in Coq. nothing more than that. And we defined some notions which are related to partial orders in this module, like what is a partially ordered set, chains, anti-chains, chain cover, what is called width, and height, means largest anti-chain in a poset. And then so to start with, we took a precise problem, a beautiful result from on finite partially ordered set. It is due to Dilworth. So it relates what can be, it actually tells you what can be the shortest chain cover for a partially ordered set. So chain cover is a collection of chains which will cover the whole poset. So it relates the smallest, the size of the smallest chain cover to the largest anti-chains, and it says that it is exactly the same. So we there are many proofs available, Dilworth, but we have taken a proof by Perles, which was much more cleaner to formalize. So it uses induction and some case analysis, and we formalize this proof completely inside the Koch theorem prover. So actually Perles proof gives you a different argument in two cases. In the beginning itself, it says this, either this is first one case 1 and case 2, and regions are different in both the cases. So we used excluded middle in the beginning itself, but it is possible to get rid of that axiom also, because all things are finite. So every property is finite, and we can replace everything with a decidable predicate and somehow get rid of this. But for the time being, our formalization uses excluded middle. And this is another theorem which is dual to Dilworth. It relates the size of the smallest anti-chain cover with the size of largest chain in the poset. So this proof is a bit easier than the first one, Dilworth. So we formalize this one also. And once you have these two results, there are many other results on graphs which can easily be formalized using these two results, because you can convert graphs into posets and apply this theorem directly to prove them. So what is more interesting in this whole process of formalizing this, we came up with some very basic facts on finite partial order that you would need while formalizing this theorem. So we organized them in form of library, and so library, as well as we somehow we did something to automate the proof search. You don't need to know now the name of lemma to apply that lemma. So that part we did in this. So Koch also has a LTEC language where you can do some proof search by just matching goal with the goal of available lemma in your library. So you don't need to know exactly, or you don't even need to go into this these files to look whether this theorem is available or not. So if it is available, it will apply, and you can immediately solve that. So the major hurdle was that this ensemble module, when you work with this module, relations occur more naturally than functions, and many a time we need, since we have a habit of talking in terms of functions, so it's a problem. So we developed some pigeonhole principle, which relational variants of pigeonhole principle. Even cardinality of set is also defined as relation in, and that creates a lot of problem. But and new definition on sets. So we gave some new definitions on set, poset, and some basic. So when using this library, so you can, when you want to say that there exists a chain, actually you have to give a proof before. So let this be a chain. Before that, you have to give proof. So there are lots of existence proof which you have to do this, and all of them are summarized in this library. Similarly, there are many finiteness proofs that is also there, and and this contains the proof of these major theorems like Marie's theorem, Hall's-Marie's theorem, Edwards-Jacob theorem, Dilworth, as well as Mirsky. So now, if you want to work with poset, probably you don't have to work out these lemmas and things. You can just directly use this one, and that's it. Thank you.
Are you reconstructing classical proof, or did you need to somehow do different proof to fit it inside code?
So you always have to do a little bit. So since here the language is type 3, it is not exactly that proof, but we are mimicking that proof. The main idea is same. Yeah, but it, yeah.
Once upon a time, I decided to check proof provided by Koch for 4 colors hypothesis. But combinatorics, axiomatization of combinatorics consists of 4,000 lines in Koch. I cannot trust to combinatorics with 4,000 lines in special programming language. Could you please comment? So I gave up the idea to validate this proof.
So I don't know about that proof you are talking about, but 4-color theorem has again been fully formalized inside Koch by Gron.
4,000.
So it doesn't matter how big is your proof here. You just need to believe.
Formalization. How many axioms did you have? How big is your formalization? Your library.
So this one is, I think, within 3,000 lines of code. Yeah. So you don't need to trust you don't need to go through the proof to trust it. You just need to trust the kernel of the Koch, whether it implements the logic correctly or not. So this library can be as big as that, but finally everything translates to term.
What is the size of your claims, your theorem, not the proof?
You show them a code. You had the code of the theorem.
No, code is very simple. It's okay. But how many lines the formalization of combinatorics itself? If 4,000 lines, it is a program in special language. Well, everyone can make mistakes. Or input in these 4 lines the intentional mistake to prove everything.
How long is the formalization of posets? How many lines?
So poset is around 1,200 line roughly.
Formalize what posets are.
Posets, some basic facts also, not only the definition. Definitions are hardly, there are 10 to 12 new definitions which we added to the standard library. But there are many facts, finiteness proofs and existence proof that we did into that, and that is hardly 1,000 line or 1,200 line.
Thank you.
Thank you. So you want to use this one? I'm sorry. Okay. Yes, this one you can. You have PPT is already on this system.
Yeah, it's already on there. Mm-hmm. It's just this one.
This one.
Yeah. Oh, can just do. Okay. Great. Thank you. Is it loading? No.
Yeah.
Okay. No. Okay, I will just start. Hello everyone, my name is Tim. I'm from the Otto von Guericke University in Magdeburg in Germany, but before explaining where Magdeburg is, I think it's easier to tell you that I live in Leipzig, what is about 120 kilometers in the south of Berlin, just to get me to know. And what I want to talk to you today is about an experiment we did where we wanted to use probabilistic model checking, not in design time, but while executing the real system. Just to have some example why this is necessary. Just think about this new emerging topic of autonomous cars and car-to-X communication. And now go a step further when you think of your parents or your grandparents and you want to park your car within a parking slot or a bit parking house. So the best idea would be to just go there with your car and say, press a button and say, okay, please car, park you by yourself. Just where the parking house tells you to park, and you do this on your own. The first idea would be that you put as much sensors as possible onto your car and say, okay, do this. But a second idea that is coming out of industry because they want to build it at the moment, or they try to build it at the moment, is that all the sensors are not necessarily on your car, but all spread over the parking house. That means when you're entering with your car, the parking house, it tells your car which type of sensors it supplies to you. That means pedestrian sensors, some sensors of where parking slots are empty, and where you can go. And then, when you do this, it becomes quite interesting because when we are dealing with autonomous driving, we're always dealing with safety problems, with safety calculations, and with probabilities that are given by norms and standards that we have to ensure when we work with this autonomous driving. And what we have to do now is not to verify the system on design time, where we say, okay, we have 6 types of failures, and when these failures fail, then we have this probability that our hazard does never occur, or with this probability we crash into another car, but we have to do this online. As we learn these days, and we will probably learn in the next days, there's this probabilistic model checking. Probabilistic model checking is very, very interesting because it can give very precise, well not precise, but the exact probability for a specific event to occur when you have a Markov chain. But the problem with this, when you ever tried some tool, is this takes very much time. That means even for small, not so complex systems, you're waiting for hours, sometimes for days to get a result. Orthogonal to this, let me call it numeric probabilistic model checking, possibly it's not the best name, but there are statistical model checking methods. That means instead of just have your Markov chain and compute your matrices and do some numerical measurement, you can just sample paths of a system for a given bound. That means to say, okay, I want to calculate the probability that a given hazard doesn't occur within 100 steps, whatever steps means with the logical clock. And then you can just compute a number of samples, say 10,000, 100,000. That's not the problem because that's very fast. And then you can calculate the mean value of that. But a real hard problem when you deal with simulation and sampling is the confidence of the value that you are computing. Because just imagine when you have a probability for a hazard, let's say a crash with the sensors with 10 to the power of minus 9. That means we would need at least 10 to the power of 9 samples in mean to compute one path that contains this hazardous situation where you can compute this value for the probability for. Therefore, we are dealing with the ray event simulation in our research. This is not new because ray event simulation just says, okay, we have the Markov chain or the Markov decision process, and then we say, okay, let us define some region of interest from which we can sample the paths, and when we have defined this region of interest, we just make it more probable for our sampling process. Then at each decision where we have a probabilistic decision, we throw a coin and say, okay, with this probability we go on this side, and with this probability we go to that state. But the problem here is we can do this, but how to choose this region of interest and how to choose the probability for your system, the new probability distribution. And what we come up with is the idea that when you have a safety system, that means often you have only just improper and countable number of paths that are leading to the hazard, and therefore often they are just sub-paths of each other. And then we said, okay, then let's just compute this path by using model checking, and then when we have this hazard path, then we can say, okay, we don't want to make the distribution, compute the distribution for the whole system, but just make it fitting right for the hazard paths. Therefore, this is just the formula we come up with. This is the variance formula for the sampling distribution. Then we said, okay, let's just minimize the variance of the sampling distribution. And what we found out is that this works quite well, even with larger systems, but there are always drawbacks when this is not the case, that all hazard paths share some suffixes. For the future work, what I just want to do is to say, okay, we use some symbolic execution or some SMT style execution to derive the hazard paths from this. So this was a bit interesting for you, even though it was more in the safety and probabilistic direction. Then I hope we meet at the poster. Yeah, thank you very much. Questions? Oh, sorry. Yeah.
To apply this method at one time, where do you get the models when you need them very quickly?
So the question was, when when you want to apply this method at runtime, where do we get the models from? Of course, this is some kind of problem. This research is embedded in a bit larger context, in a bit larger research project we did, where we are developed some method, some lifecycle method to integrate this complete model-based verification to the design of the system. And from this, we can say, okay, we have these models at the time when we are on the system, because you have your static model, you have your system model, and of course you can also have your failure model, and then you can just compute this on runtime by just changing out some sensor information and some failure probabilities of the sensor. So that's the first idea. Yeah.
So, model checking in real time. I believe model checking at real time can be done only a posteriori when you already have a trace. And so, okay, let's assume, so model checking says either yes or no.
Yeah.
And so let's assume it says no, so what's next?
Okay. Well, the first point is, I've left some points out on the slides that I had on before. The second idea is to have some evaluation on learning the behavior of your model. That means you just have all the computation of the distributions, and then you can change out just some failure models, some failure automata for the system, and then this computation is quite fast. And the next thing is, when you're dealing with probabilistic model checking, it is not the case that you have yes or no, but you have some number. At the end, of course, there's some hypothesis or some probabilistic threshold you have to ensure. But the question is, normally when you do this at the moment, then you have to check this before. And then you have to say, okay, when the sensor is not available, or when I have this specific system, and when the setting changes, then I cannot say anymore whether this holds or not, and so I cannot use the functionality. But now you can deal with different new changing environments and calculate, okay, I can ensure the probability that this hazard does not occur with the 10 to the power of minus 9, and then you can just...
So you recompute the probability.
Yes.
But it's not model checking, because the model checking means checking a model against some property.
Well, this is...
I would call this model improvement or model refinement.
yeah, well, this is it's called statistical model checking. That is that's the name of this.
But what do we check?
Well, I have a property. In the simple case, I have some reachability property, some bad state you don't want to reach, and for this you can calculate the probability for reaching this bad state.
But do you check the property itself?
Well,
You can see it in that way, you check how good a property is satisfied if it's with
Yeah.
the reachability condition. The probability
Yeah.
gives you some value between 0 and 1.
Yeah.
Indicates how good.
Okay, let's assume your system satisfies your property not so well, or in some bad way.
Well, but this is not your problem. Well, the point is, this is some kind of hypothesis testing at the end. So you have some probability that is given by the government or some norming authority. They say, okay, you have to ensure this probability for your system, for your safety, system safety, and then you can check at the end whether your property, your PCDL property, is something like this. So PCDL, you can write, for example, a question mark, then it calculates you the probability, or you can put some threshold on it, and then it says yes or no whether this probability holds, whether this property holds with this probability or not.
Okay, I believe you are right.
Okay.
Good evening, everyone. I'm Suguman Bansal. The work that I'm going to present today, called Comparators, it's been done in collaboration with Professor Swarat Chaudhary and Professor Moshe Vardi, all three of us from Rice University. In my talk, I'll mostly try to motivate why we require this new technique called comparators and briefly touch upon our results on it. And I'll be very happy to take questions about the results after the talk. So, over the course of this winter school, we've been hearing about linear traces a lot. They appear in LTL, they appear in transition systems and whatnot. In this illustration here, every single arrow denotes one transition, and the alphabet next to it is basically the alphabet of the system. So what is a linear trace? It's basically a sequence of transitions. A variant of this would be one in which every transition is also associated with a weight. In this illustration, the weights are given in green. For example, in the first transition on alphabet A, the weight of the transition is 5. Now this is a quantitative linear trace, which is not fundamentally different from a linear trace. But because it's a quantitative linear trace, there are certain more features of interest. For example, we'd be interested in what is the weight sequence of a trace. And that's nothing else but the sequence of weights of transitions along the given trace. In this example, it would be 5, 6, 1, 2, 3, and so on. Once you have a weight sequence, you'd be interested in what is the weight of the trace. And for that, we require an aggregate function, which takes as input the weight sequence and returns a real value. So we'll always have an aggregate function. For simplicity, we'll assume all our weight sequences are natural number sequences. And then the weight of the trace is nothing else but the function, the aggregate function applied on the weight sequence of the trace. Now, before you think this is esoteric, let me try to convince you it's not. Quantitative linear traces appear in all sorts of existing data structures within formal methods. The most common one being weighted automata. A weighted automata is the regular automata that we've been studying at this winter school, except that every transition is also related to a weight. For example, it has its regular states such as S, T, Q, transitions on alphabets given in red, and the digit in green is the weight along that transition. And now it's not very hard to see that any run in a weighted automata is really just a quantitative trace. So quantitative traces appear very naturally in many data structures. So it makes sense to study them and study the fundamental operations in them. But what is the fundamental operation on a quantitative trace? And I would argue that the most fundamental operation on a quantitative trace is the comparison of their weights. What does that mean? Well, if you're given two traces, for example, trace 1 and trace 2, and an aggregate function f, then the most fundamental operation would be, can you tell whether the weight sequence of one trace is less than or equal to the weight sequence of the other? Now, to convince you why I believe this comparison is fundamental, let's look at some basic, let's go back to the weighted automata example, weighted automata scenario, and see how comparison naturally falls into very simple questions there. Let's look at how a weight of a word in a weighted automata is defined. Well, because there's non-determinism, every weight may have multiple runs, hence multiple quantitative traces, as a result of which there might be multiple values of the weights of traces. Which among those would pertain to the weight of the word? One way to get about it is by saying that the weight of the word is defined as the supremum of all the weight of its traces. So now that you're looking at supremum, you understand that the underlying fundamentals is really that you're comparing the weight of these sequences. So comparison appears very naturally. If you look at a slightly more complicated example, we spoke about language inclusion in the winter school. The variant within weighted automata is that of quantitative language inclusion. And all this says is that, well, in language inclusion, the inputs were two Booke automata A and B. In quantitative language inclusion, the inputs would be weighted automata A and B. And the question it asks is whether for every word, the weight of the word in automata A is less than the weight of the word in automata B. So once again, we are really just comparing the weights of traces. Hence, comparison is the most fundamental operation on quantitative traces. However, how do you think? I mean, if we want to compare the weights, we probably need to calculate the value, right? But there's a fundamental issue here. our weight sequences, our weight sequences are infinite sequences. Hence, it's not very possible to calculate a function on those. So, for example, if you want to look at, suppose we define the function f, the aggregate function, to be the one which returns the integer that appears infinitely often, the maximum integer that it appears infinitely often. You cannot look at a finite trace and determine what the value is. So, although comparison is fundamental, it's extremely challenging because the explicit calculation of weight of an infinite sequence cannot really be done. And that is where we step in. What we propose is a technique that we call comparator automata, which can compare the weight sequences, compare the weights of traces without explicitly calculating the value, explicitly calculating the weight. What it does is that it reads both the weight sequences at the same time, and in an online fashion, it can tell whether, can that turn off? Thank you. It can tell whether the weight of one sequence is less than or greater than the other one. So formally, a weighted automata is an automata. It's defined for an aggregate function f. Its alphabet is over digits, over natural numbers, over a pair of them, and it accepts the pair of weight sequences a, b, if and only if f of a is less than or equal to f of b. So if a pair of sequences are accepted by this automata, we know that the weight sequence of a, the weight of a is less than that of b. And this automata could be a Pookie automata, it could be a Pookie pushdown automata, and depending on what the aggregate function is. I'll quickly go over some interesting aggregate functions. I had to have one more slide. I'll quickly go over I'll just go over one interesting aggregate function.
I don't know, if it's 6 minutes, unless someone wants to ask.
Okay. Can I just finish this slide?
As part of the question, you can do it. But it's
Okay. Please go ahead.
First question is, why does the range of your function, like, is a real number? Why is that?
The range of the function. So f takes as input a sequence of natural numbers and returns a real value.
How? So, I guess, wait. And f is aggregate function. So,
Yes.
so I see. We didn't define that. Fine. Next slide. Okay, explain this. Go ahead.
I think I can stop there. Do you have a question?
So how does this weight differ from how we learned about reward in probabilistic verification lecture this morning? I mean, since I know that reward is annotated on a state, and now here your weight is annotated on the age. However, we could always translate, I mean, this automata with weight on age to somehow another automata with reward on state. I think this is possible. So how does this differ from how we learned this morning?
So what you're talking about is so the way to think of it would be what you're talking about is a specific aggregate function, but what we're defining a comparator automata, it's a very general notion, and you would want to construct a comparator automata for a given aggregate function. So in your case, the aggregate function is this probabilistic measure, and there would be many more interesting aggregate functions that one would be interested in. All right. Thank you.
Okay. Hi, good evening. My name is Tiago. I'm associate professor at this university here in Brazil, Federal University of Campina Grande. I'm glad that I'm the student spotlight. It makes me feel much younger. I want to present work that is actually being done by my PhD students called Alison, and with cooperation with another professors called Rohit. If you allow me, I'll make some publicity, just a small one. We're having this 21st Brazilian conference on formal methods. I'll be sharing next year, the committee. So we published the papers as all in English, although it's Brazilian, but the papers are all in English. And we have lecture notes on computer science, so for publication. So if you want to go to Brazil and go to Salvador, which is the city of the next conference, please let me know. This is the problem we're trying to tackle here. How many of you are familiar with the OR logic here? Everybody? Okay, great. We have this pre and post conditions for an imperative program. So one way of implementing this right now in object-oriented languages is doing some kind of design by contract, which you have some different frameworks and languages for doing this. For example, we have this Java modeling language in which we write pre and post conditions for any method. For example, in this debit method, we don't want the amount of being negative, and you want to ensure that the balance is the same as the older one without the amount, and the result would be this balance. So this is a way of actually trying to do this in general purpose languages. But what we say is that forget it. Developers don't do that. Okay, they don't want to do that. This is too much work. They are agile today, right? So one way of doing this is actually taking a look at these APIs or interfaces that have this bunch of documentation written in plain English. So it's usually the only documentation for this language, for these libraries, and try to suggest contracts from that one and use it for some kind of check-in. Not really a verification, but maybe trying to get from these written documentation some contracts. For example, a very simple one, maybe we can get from this text here that requires that this variable should be different than null. So what we're doing here, actually we're trying to get or extract these contracts from this commentary and see if you can use it for some kind of verification. In our approach right now is actually trying to use some machine learning algorithms for reading this, actually extracting this text and getting from some training, supervised learning actually, some training with answers that we provide manually from reading a lot of API documentation. Actually, we have a database of 137,000 small contracts. Actually, we actually made a very simple algorithm for making a first filtering, and then later we actually manually checked and classify it. So we use this for making a measure of how these algorithms would perform in some of these open source APIs that we are trying to test. So we have this 3 algorithms here: Adabus, multi-layer perceptron, passive aggressive. It's a great name for an algorithm, I can say it, which is the ones that are performing actually best. But not really, we're still analyzing why this is happening actually, but this one seems to be very good at actually extracting the text and try to analyze the semantics of the text and try to get the contract from that. This is having a lot of, these algorithms have, for now, they have good results and accuracy, precision, and recall. So our next step here is getting this Java big APIs, which the only documentation is written comments. And we're going to generate the contracts running this solution, generating these contracts, and then actually try to run generated test cases based on the oracles. The oracles of these test cases will be the assertions that will be generated by our contracts. And then check this API implementation. We actually did that already, and we already have found 2 inconsistencies actually in this reflection API. What is an inconsistency? It's something that is written in a documentation, but it's implemented differently. So this, we don't know if it's a bug, but it's an indication of the bug. Okay? Thank you.
How do you label the examples from the benchmark you mentioned? You said 137,000.
Yeah, what we did, we get this open source libraries with the documentation. We wrote a very simple algorithm for actually separating from simple synthetic analysis of the text in nullable and not nullable, for example. Just one example. And then we go through this data and actually did some corner cases in which our algorithm wouldn't work. So we did it manually and separated those in these 2 sets. So we actually had to do this manual work. It took like 2 months, 3 people doing it.
Although benchmarks or 137,000.
Yeah, these are open source systems with commentary. It's just we have like a 30 to 35 systems with a lot of commentary. Yeah. Yeah.
So, are you doing it for only the null properties?
Oh yeah. This is our first example is actually doing this for the nullable properties. But we want to do this for other kinds of contracts, like arithmetic contracts, which are the most common contracts, actually. Nullable and value. They test the value of the variable.
Okay. Okay, so hello everyone. I'm Pedro Valero. I'm doing my PhD right now at the Indea Software Institute in Spain. And I just want to tell you a little bit about my last work that I have been done. I'm not going to explain the details. I just want to show like for me, fascinating results that we have obtained. So we wanted to develop a tool to perform regular expression search on compressed text without having to decompress it. I think it's pretty clear why this problem is important, because like big companies, they handle huge amounts of data and they want to manipulate this data. For that, they need to do regular expression search. But because they have a lot of data, they need to keep it compressed somehow. So right now, these two problems, regular expression search and compression, has been studied and analyzed like independent problems. Right now, the best engines, we have a lot of really good engines and programs for regular expression matching and also for compression, but they work independently. However, we found that there might be a way to combine those ideas to make a better tool. And that's what we have been doing. So we developed a tool called search with the set, because it's just search on the compressed text. So the main idea of our program is that it has a mathematical foundation, it has a theoretical foundation, we can prove that our algorithms are correct and so on, but it's actually working. So we can compare and compete with real world applications. So I'm just going to show you like the result that we have obtained, and for that we have decided to compare with these tools. So basically we have grep, which is like command line tool that comes with any Linux system. We are always considering the last version of everything. And we also have regrep, which is another tool newer than grep. It's implemented in Rust, and it was like the best tool at the time when we choose to use it. Then grep updates and then become a little bit better, but they are there like competing each other. So as we are going to search on compressed text, we need to also compress the information, and for that we are going to consider these three tools. We have gzip, which is the standard one that comes with any Linux system. We have repair, which is a grammar-based compressor. Which is the one that you have to use if you want to be able to search with our tool. By the time being, we could extend it to other tools. And then we also look at the CSTD, which is like the latest tool for compression. It was developed from some people of Facebook, and it's actually outperforming the gzip. So right now, when people want to search on a compressed file, what they have to do is to decompress it and then doing the search. The best way to do it is doing it in parallel. You have one process decompressing the input, and then you have another process that search on the input, which is streaming from one to the other. And we do this with these two tools, which decompress. We look at that file compressed with this CSTD algorithm, and then decompress it and search with grep or with regrep, each of those. And then we also have our tool. So the result so this is the result we have obtained. Let me see if I can. Okay. So we consider several regular expressions that are described here. It's just a bunch of expressions that I just made up to show that we are working efficiently in most of the cases, let's say. And the results are here. We can see that for each regular expression, how we behave compared with the others. But let's say the interesting part is the last column, when we compute the average of all those values. And here with these black boxes, we represent the confidence interval with a confidence of 98%. All right. So we can see from this result that our tool is actually we are searching on 100 megabytes of English text, some subtitles, and our tool is performing faster, for instance, than regrep, even though regrep is searching on the original file. So you have to keep the 100 megabytes of text and search with regrep, and then we are faster than that just by handling the compressed file. If we compare with grep, we can see that grep is slightly better than us, but then if you want to search on a compressed file, you find that, again, with regrep you get worse result than with our tool, but if you want to search in a compressed file with grep, you will find this without our approach. This is the best you can do, and we cannot say that they are clearly better than us. There are cases where we outperform them and vice versa. So the idea here is that we are comparing our tool, implemented just by myself in some months, with a great tool developed by teams of programmers and from big companies, and like state-of-the-art implementations. So the idea behind that is that our approach is actually really interesting and it's promising. For getting more details about it, just come by the poster and I will explain the details. So we can see another graph here where we are, because we are searching on a compressed file, the way the file is compressed has some impact on the way we perform. So here we have another example where we take some log files, again with size of 100 megabytes, we compress them and we did the search again. And in this case, we obtained that we are actually being faster than all the other tools that search on the compressed text. Recall that this corresponds to our tool that is not using any parallelization yet, although we think we could use it, and while these guys are using this parallelization. And just to conclude, let me show you another graph to illustrate what's the gain you obtain by using our tool. So we have here, this is a graph where we get some instances. We have run some search on some files, and we are each of those points correspond with the time required by some tool, just grep searching on the original text or the searching on the compressed file, against the time that it takes for our tool to perform exactly the same search, giving the same results. So the lines, the dots that are below this line are cases where they are faster than we are, and above it means that we are faster than them. So we can see that if you keep the file in its original form, you just keep the text file, you get some performance with grep, but if you want to keep the file compressed, then you get some penalty when you want to process it. And it's this penalty is the difference from the time required by when searching with grep with the time required when searching on the compressed file. And the idea is just that with our approach, you can keep the file compressed, but you are reducing the penalty that you are suffering when for doing that fact, and then you get this line, which is kind of in between the other two approaches. Thank you.
There has been quite some work on querying compressed XML documents.
Sorry, what?
Querying compressed XML documents.
Yeah.
So taking XML, which is
Mhm.
just text, and compressing it, and then running queries on the XML again without doing the compression.
We haven't done such experiments yet, but if you can describe the query as a regular expression.
No. Well, I'm asking, are you aware of this work?
Yes, I'm aware of that. But
you're aware.
Mhm.
How do your techniques compare to the?
No, we haven't compared with that because to do that you should first describe the query as a regular expression. And okay, this work is not concluded yet, so we are still working on it, and we haven't worked on that. We haven't done that experiments. They require a fair amount of work to express the queries as a regular expression.
Could
Yeah.
you go back to the experimental result, the chart?
The previous one.
So this one. So the result obtained by grep is the input file is not compressed, right?
Yes.
So those four bars, their input size are different. And
Yes.
So it's 100 megabytes before compression.
Before the compression.
So how large is?
Okay, it depends. For these subtitles, it was kind of maybe 25 megabytes.
How do you expect if we give a larger input file, like maybe a 1 gigabyte or 10 gigabyte? How does this compare to grep?
We have done some experiments with bigger files, and kind of the comparison of the performance remains more or less the same. We just choose this file, this size because it was easy to handle, but it's not a great difference. Anyways, the problem is, for instance, with this repair algorithm, when you want to compress these gigabytes, it's quite hard.
We discussed this, so you have to rely on the dictionary and produce some grammar, right? So if the compress itself become more difficult, then will your method got influenced by the difficulty of building the dictionary, building a grammar from the dictionary?
No, once you have compressed the file, doesn't matter how long it takes. I just have a dictionary, which is a grammar describing the string, and I will handle it. There is no big problem. The problem was to generate the files and to run all of these experiments. This is just a graph that we have considered different kind of files, like CSV files, JSON files. So we were, again, this is not the concluded work. This was just the result that we have right now. Maybe we can present it better, but that's the current state of the project right now. Okay, thank you. Yeah, I was the last one.